Feeling the heat?
It's actually really nice outside.
It's a little bit drier heat now, so it's a little nicer, but still it's getting to you, isn't it? So I went to London a few years ago, and it was in the summertime, and they had a heat wave. And London is a very old city, and it's been well engineered and put in place there. Lots of people live there, and they can live a range of normal city lives. And over the course of the week that I was there, all of the downtown buildings in London slowly got hotter and hotter inside. The reason for that, and it became very uncomfortable for everybody in the city. And the reason for that was the heat wave that they had in the summer, like we're having here. The heat wave they had in the summer was to higher temperatures than they are used to. And engineers, being smart people, had built all the air conditioning in the city to handle London weather. So when the weather got hotter than London weather, the buildings could not cool down sufficiently during the day and overnight to handle the heat flux coming in. So if you think about the outdoors, there's the solar radiation, the black body radiation coming down and hitting things. And then there's the conduction from the building into the air and the ground, and also the black body radiation of the building out. And you can do an energy balance and a power balance. The other element that gets added into that is the air conditioning system. And a typical air conditioning system moves air through a tube and has a refrigeration unit where the air passes by some cooling panel of some kind. And what happens then is the air comes in at one temperature and it goes out at another, and air conditioning then is, you can think of it in a simple way as having the ability to lower the temperature of the air passing through it by a given delta T. Suppose it was 10 degrees. And then as the air circulates again in the building, you might get a little cooler temperature and a cooler temperature, and it'll reach down to where it shuts the thermostat off. The problem was that the air temp coming in had so much heat load in it that the air conditioning designs couldn't handle that over time. So they were providing a delta T, but if you're starting with air that's 90 degrees instead of 80 degrees, it's going to come out hotter by that difference in temperature. And the heat load was such that the air conditioning capacity that was in the buildings couldn't handle it. So by the end of the week, it was miserably hot inside all the large buildings in downtown London. Misery, right? And yet the engineers were smart, but they could not plan for or put enough capital in place to solve all possible circumstances. Another example where that happens is earthquakes. So we live in a part of the world that has a sizable amount of earthquakes, and you feel fairly safe sitting here in this building, don't you? And why do you feel safe in here? Because the engineering for the building is relatively good, because we have relatively large amount of wealth that can be applied to building infrastructure costs. And we learn from the earthquakes. Now, we don't know everything there is to know, so we still will make mistakes in the buildings, and we still will have additional things to learn. But there are large parts of the world that have earthquakes and do not have the wealth to be able to make the stronger buildings. So they are going to suffer more human damage in earthquakes, and it's a terrible thing, but they just don't have the money to be able to build fancier buildings. So whenever you're doing your engineering, you have to take into account the possible as well as the science that you've learned in somewhere like a class like this. So you have to combine where's the best use of those resources for things. All right, so let's go back slightly into last lecture's material and then weave forward from there into the material for the rest of this lecture. What we found was currents make magnetic fields. We found, for example, that a current going downward like this will have a magnetic field that wraps around it in a circle for each of the field lines and progressively weaker as we get further out. The magnitude of the field falls off with radius away from the wire, and it falls off as something like 1 over r. And then you ask, oh, what happens if r goes to 0? Oh, if r goes to 0, wait a minute. The current is carried in a wire that has a finite size. So r doesn't go exactly to 0 with the current still at a radius enclosed. When you arrive at the wire, now the current's distributed in the wire. So the B field builds up as you're getting in close to the wire, and then the current is distributed so it doesn't actually keep going to infinity, it flattens out. Just like if you had a sphere of charge that was distributed throughout the sphere, the electric field builds up to the edge and then it continues to rise inside, but now it doesn't go to an infinite value because the charge is distributed. And then you go, oh, well, that's great, McWilliams. You gave a macroscopic picture that's fine, and I see how the wire has the current distributed so it doesn't go to infinity. But take me down to the microscopic picture and put me on an electron. And I got that electron going along, and it says that B is going to go as 1 over r squared away from that electron. So if I got in there at an infinitesimally close to the electron, the B field must become infinite. And I go, well, yeah, I guess the equations, we don't know what happens there. So we don't have all the answers on these things. But on the macroscopic picture, we've got a very good description going on, and the integral level, where we've got macroscopic things, works great. But sometimes we get smaller and smaller and smaller. This stuff eventually breaks down in some way that these kind of equations don't give us the full picture. Okay. So if I took, now that's a straight wire. So this is, now let's take, instead, let's have a circular wire. So I've got a wire that's coming around in a circular loop. And so this is a loop of wire. So let's do it where it just is like that. So it's a loop. Imagine it coming out towards you, okay? And the ring of wire like that, and we have some current. Let's have the current coming out here and going in at the bottom. So the current is going the same way, clockwise from my perspective, out towards you at the top and in away from you towards the bottom of this drawing. What's the magnetic field going to look like for such a loop? Each element of current makes a contribution to the magnetic field. Let's look up here at this top piece. So if the current is coming out, it's going to have a contribution to the magnetic field from that top element that looks something like that. And as the current goes in at the bottom, it's going to have a contribution that looks like this. And remember, the magnetic field falls off with distance away from the contributing portion of the current. So if we're looking at this from a side view, we have our current flowing around something like that. Then on this point right here, maybe that's the, well, let's look at it here. We'll put it up here. This is the top part and the bottom part. The top part is going along, and it's going to have magnetic field coming out of the board here and going into the board there. And this bottom contribution is going to have a similar contribution to the magnetic field. So the magnetic field is built up now progressively from each of these contributions. the next one builds, the next one builds. They all contribute all the way around. What we see inside, these guys are all pointing in the same direction inside the loop, aren't they? And outside the loop, this one's pointing downward into the board, if you wish. But this guy makes some contribution over here also. And this guy's contribution over here is pointing out. It's in the opposite direction. So what we have, let's put B top, and now here's going to be some B top down here. But it's going, and this is, we'll call this the bottom one. But B top down here is going to be less than B bottom because the contribution from that top element is further away in distance. So they don't cancel, but they are in opposition. It means that for this kind of drawing, if we have this loop, that the field will be stronger inside, going like this. If we have the current, let's see if I got coming out, yeah. And weaker outside. And what we see for the magnetic field lines is a spatial distribution. Conceptually, all of the magnetic field lines you're seeing pass through the center of the loop. And all of the magnetic field lines that you see pass through the outside region, outside the loop. Look at the area difference. Inside the loop is the area, say A, pi r squared. Outside the loop is the rest of the universe. The area is very large. So the magnetic field lines are concentrated on the inside and much weaker on the outside. But not zero. But not zero. And we have a dipole field. Again, B is a dipole. Now, let's construct a solenoid. Conceptually, isn't that a neat word? I don't know the etymology of that word. That's really neat. A solenoid. So we're making a bunch of coils like that. And we put some current in. And the current comes out the other side and goes off to whatever battery supply took care of this, whatever resistance. And we have a wire that's making a series of loops. For example, do we see such a thing right here? I just happen to have a solenoid on me. Okay? And did we have a solenoid yesterday? A bunch of wires? And how many turns were in that? 3,250, the magic number of the day. 1,000 pi. Okay. Do you see 4 more coils here? And how many turns would you guess these coils have? Don't they look like the one we used yesterday? I wonder if one of them is. I don't know. Okay. Now let's do this same idea. Can we find out what the magnetic field should look like here? Yes, we can. Is this complicated? Would you like to add up the contribution to the magnetic field from each little dl in there and do the integral along this coil like that? Doesn't that sound like a miserable experience? Is it possible? Yes, even without a computer, it's possible. Is it a miserable experience? Yes, I have done it. It is a miserable experience. It takes many hours to do it. And I'm not going to do it again. I'm going to tell the computer to do it now. Okay? So the wire comes along and then does its loops. So let's imagine each of the loops. Each of the loops is like one of these coils. One coil right there. So each of these loops makes a magnetic dipole and makes a magnetic field structure like we've been drawing. So what we need to do to find the total magnetic field is add up the contributions from each of these coils to figure it out. How many coils do we have? Whatever the number is, right? So we've got this many coils. And do we see some kind of distance here? Let's use a length. So we have n coils in a length L. We look at this guy, and it makes the dipole field. The field is concentrated inside that one coil and weaker outside. It's going one direction inside, and it's going the opposite direction outside. And so now let's imagine adding them up. This coil and this coil. These two right next to each other, they're very nearly bumping up against each other. It means they're going to add pretty much like, almost like doubling that, right? But what about this guy down on this end and this guy way over here? Now the field lines from these guys are going to have some contribution down there, but not very much down at that end. And the contribution from this one end coil down in the region of the other is going to have some bend to it. It's going to have some angle to it. Overall, the strongest part that we're going to have is going to be a magnetic field that adds up from all these guys to be coming through looking like this. Nearly a straight field down the center, each coil adding on to the next one, and all of the angular differences going away with distance. And then the field line will wrap around and come back. So this is our B field. That's the structure the solenoid will make. Now you remember, for making magnetic fields, that we have a mu naught here. You don't get very much magnetic field per amp. So the reason we go to all this trouble to make so many turns is every time you add another turn, you're effectively adding more current. Because you get the current going through the first loop and the current going through the second loop, doubling, and so on all the way down. So if you can get a lot of turns, you can get more magnetic field. Now, magnetic field is concentrated in the center and weaker on the outside, but not zero. It's weaker, but not zero. The simplest way to look at this thing is to do a simplification. We're going to say that B is B inside and the solenoid. And we're going to say that B is approximately zero outside. But we know it's not true. So this is an approximation, a simplification. It does mean that if you make your magnetic fields inside and then you go hunting around right outside the coil for the magnetic field, on a typical solenoid, the magnetic field outside is only a few percent of what's inside. It is mostly inside, but it's not zero. So if you're doing things that matter on small fields outside, you've got to keep a track of reality instead of this simplification. And if we have this simplification, it's really easy to see that the integral then goes to B, the dot direction. The dot, we're going along. Let's pick a path to do our integral there. Let's pick this path to be this dashed line. So here's our Amperion path. And that Amperion path then is where this closed symbol on the integral is being followed. This is the path we're going to follow. So we go along this path out here. dl is this way. And in here, dl is this way. So I chose it to have dl pointing in the same direction as b. So what's that dot product going to do for us? If dl and b are in the same direction, what happens to the dot? The cosine of theta is 1, and we have b times whatever the length is going along inside. And outside, b is very small, so we ignore that contribution, and we estimate the magnetic field times the length of the solenoid is mu naught, and how much current is enclosed? N turns times I. And that little dot next to it is somebody's knuckle in the chalkboard. It's not a period, okay? So what we're seeing is a solenoid like this makes magnetic field according to the number of turns per length in the solenoid and the current that flows. So you'll see that written sometimes like that, where N is the turns per length, turns per meter in the solenoid. That makes sense. If we can concentrate the turns into a shorter length, we'll get more magnetic field because there's more current nearby. The closer the current is to where you're looking, the stronger its contribution to the magnetic field. Makes sense. The solenoid could be some long tube like this, and that makes the integral very easy to do and to figure out the magnetic field. And wasn't that easy compared to adding up each little dl and doing it around the whole loop? Sure. Now suppose I wanted a different shape. Suppose I wanted it to be in the shape of a bagel. Today it would be a good idea, right? And so if we want to make a shape of a bagel, I could take this solenoid and wrap it into a circle. Take the whole thing, make the coil like that, and then go man of steel, right? And do that thing. Or we could just wrap it in a donut shape, bagel shape to start with. So you can make these solenoids in different shapes. A coil like this is easy to make. You just put it on something, hold your wire, and then spin the axis of whatever you put it on, and that makes a solenoid. Magnetic fields are made by currents. How many turns you have is a good thing for increasing the magnetic field. Okay. Now let's take a look at what happens. We saw last lecture that changing magnetic fields, that is time changing, right? Time changing magnetic fields make electric fields, voltages, currents, depending on what you're looking at, right? If there's a charge that can flow, we can make a current. And we saw that the induced EMF around a loop, that there was an induced electromotive force, was related to the time-changing magnetic flux through the loop. And we said we could describe it like that. And we call this Faraday's law. That's the name for it. Oh, there's an attack of sneezes in the audience. Gesundheit. Let's see, n Gesundheits per square meter of a Gesundheit flux. Okay, so we saw that changing currents induce, or changing magnetic flux induces voltages. Let's look here. Before the solenoid has the current flowing in it, there's no current. Now we turn the solenoid current on. The current goes from 0 up to some value, doesn't it? So let's put our solenoid, but now let's add a battery to it and put some voltage. When we have the switch open and nothing's going on, what's the current? The current is 0. So versus time, the current flowing, 0, and at some point we close the switch. I hear command. Please instruct. Okay, so the current will go up, and at some point it will become some value that we're talking about here. How much current would it go to? Maybe we should add a little realism in this circuit. What do you think? Should we put a resistor in over here? Let's do that in our minds, but not put it in the drawing at this point. We know there's some resistance in the circuit. So that, well, if you look at it later, you better have some. So there's some resistance in the circuit, but I don't want to pay attention to that right now. When you turn the current on, it's going to go from 0 up to whatever its final value is. What happens in between? That's our question. It can't jump instantly. It's got to do something where it rises up over time. There is a time that it's got to do this. So what's happening here? When we start to put current in, it starts to make magnetic field. When it's starting to make magnetic field, close the switch. The magnetic flux starts building. In the coil, in the solenoid. If it's starting to build and building, is the magnetic flux constant? No, it is not. d phi dt magnetic is not 0. It means it will make a back EMF. It will oppose the building up of the current. So the current cannot build instantaneously. The voltage has a voltage back EMF that's related to the rate of change of that magnetic flux as the current is building. So it's going to take some time. What we're doing then is taking time to construct the magnetic flux that's inside that thing. Yes?
Do all circuits have a solenoid?
Do all circuits have a solenoid? No, all circuits do not have a solenoid.
So if there's no solenoid,
Okay. So if there's no solenoid, what happens? The same kind of reasoning will apply, but you'll have to find what that level of application is. If we had fewer and fewer turns, there's less and less flux that could be opposing, right? So if we made fewer and fewer turns, the effect of this back EMF would reduce. So we would look at the circuit that we're building and say, is there something which creates magnetic flux? And if magnetic flux is created, then there is a d flux dt, and we look for what contributes to this term. Seeing it as the solenoid right there makes it real clear to you. But let's imagine a different way. Let's just look at this same circuit, the loop. And now instead of all the coils in the solenoid, just make it be a straight wire across the top. All it is a loop now. If I start to turn the current on, I still have, in this circuit right here, a giant loop, one loop of the circuit. And as I start to turn the current on, there's magnetic flux through this entire loop. So we still have a changing magnetic flux in time. We still have this issue. If we use the solenoid here, it's much stronger effect in here than just the overall loop. It's the ratio of the areas and the number of turns kind of thing. So you can think of it conceptually in this circuit as being primarily in this solenoid. But sometimes people design these things and the outer loop of the whole circuit actually matters a lot too. So you're just always looking for where is magnetic flux actually passing through a loop. And if it does, it's going to make some kind of back EMF. So you cannot turn currents on instantaneously, period. You can't do it. There's always going to be some kind of pushback, if you wish. But as we turn the current on, we are building the magnetic flux in time from where the close of the switch, and it's going to build up to some value as the current builds up. The total magnetic flux. The total magnetic flux, so phi magnetic total, is produced by the current. How much flux do we get per amp when it's settled into the flux built up? How much flux do we get per amp? How much do we induce in magnetic field per amp? And that is called inductance. To induce the magnetic flux using a current. And we're asking how much magnetic flux can we make? How much can we buy per amp? So this is the equivalent of deciding the ability to store charge as capacitance. This is the ability to store magnetic flux per amp. How much magnetic flux do we create per amp? You will also see this written as N phi magnetic over I, because that emphasizes the number of turns that are involved in a coil of some kind. It really means on the top the total magnetic flux. So you want to do either of these ways of writing it. Your textbook uses the lower one. You want conceptually to think of the higher one. Okay, we also know that the induced voltage is the magnetic flux changing in time with a minus sign to tell us it's opposing. The total magnetic flux, oh, that must be L times I. So we have that's going to be and this has a sort of simple kind of engineering interpretation to it. The induced voltage is minus L di dt. The bigger the inductance, the bigger the opposition to the change in current. So the change in current builds voltages, and the inductance tells you the proportionality constant. That proportionality constant, L, you can see from our circuit drawing up there, depends only on how the flux is built up. And how the flux is built up depends only on the geometry of the coil or the circuit you're building in some way. So L, just like capacitance, C, dependent only on the physical geometry of the circuit you built. L depends only on the physical geometry. So when you get a calculation for L, it's got to have no I's left in it, no current left in it, right? It's got to depend only on size and shape of things, number of turns per unit length, something like that. Okay. Let's take a look here. Somebody to help out. Do we have a eager volunteer who has not helped yet? So further back I go, I'm more likely to get. You've helped, right?
Yeah.
Have you helped?
Yeah.
Yeah. Have you helped? Would you care to help right now? Okay. All right. So come on down and. And I think probably it'd be best for them if you're back here. And I'm Roger McWilliams.
Amanda.
Amanda?
Nice to meet you.
Hi there. Okay, so what we see here to start with, you probably don't remember this, what this is. This is called a Variac, a variable supply, voltage supply. So it's a battery-like thing, but it's plugged into the floor. And what happens when we rotate the top up here, see the needle goes around from 0 to 140 on its little markings, right? As we go around and rotate this, inside is a coil. And in that coil, all this 120 volts is there, but the top part, as we rotate around, touches different parts of the coil. And so if it's down at 0, it's touching close to the starting point on the coil, and the voltage rise to that point is very small. As we rotate it around, it goes around on the dial, it goes to where it can see the full voltage by going across the full coil. So this is a way of making alternating voltage and alternating current with the ability to vary the total voltage we're putting out on this side that's heading towards Amanda. We can go from 0 up to some bigger number, okay? So let's now see. As we come out of here, the red line goes over here to what? What do you see? Oh, then he's
to the black.
Yeah, connected to the black. That goes over to here, right? And what do you? Can you describe what this is?
It's some coiled wire.
Coiled wire, and is it copper? Do you think? Do you have much experience with copper? Probably not, right? Okay, so copper is used in a lot of plumbing, and also in some kind of cooking ware. Copper is poisonous for some cooking purposes, but it can be on the outside of pots because it's a very good thermal conductor, because it's a very good electrical conductor. So there is a brand of cookware called Revere ware, after Paul Revere, that guy, you know. And no, he didn't. I can't do that. How do you do that Gangnam thing? Wasn't that it? Was that it? Can one of you do that? Do you know how to do that?
No.
That was a quick, easy answer to find, wasn't it? Even if you did, you're going to say no for that, right? Okay, so anyway, Paul Revere was a metalsmith and made copper-covered cookware that's still purchasable. The company still exists. Okay, so off the black wire it comes in, and you can actually see it going into the coil, huh?
Yeah.
And so it makes lots of turns, and you might even be able to guess how many turns. How many would you guess on the number of turns? Just give a guess.
2,070 turns.
2,070 turns? Wow, what a good guess. And it has apparently some resistance also, doesn't it?
Yeah.
What's it say?
18.5.
18.5 ohms. Mm-hmm. And that must depend on how hot it is, right? Okay, so then the coil, after the current might pass through the coil, would come out the other side and go to what?
It's clipped to the light bulb.
And the light bulb is screwed in, and it looks like a regular old light bulb, right?
Yep.
Okay, come on over here. Throw the switch. And what do you see?
I don't see anything.
Nothing happened, right? Okay, so rotate. Now leave it switched on. Turn on. That's good. Now rotate the switch. Keep going. Amanda made light inside small bottle.
Can I turn it all the way?
I don't know. Let's do it after we do the rest.
Okay.
Because I don't know, maybe it's too much for that bulb. And I only see one bulb here. So at the end, we'll see if we can break it.
Okay.
Okay, so now let's turn it off. Cool. Turn it on. Turn it off. Turn it on. Amanda makes switch also. That's amazing. Now, did you see how bright it is, right? And how easily it turned on? Okay. What is this? You got it? Mm-hmm. Okay.
It's like a set of rods.
A set of rods, maybe like iron rods. Okay. Okay, so now I'm feeling a moment of irony. Take this rod. Let's just show them how the switch works. It works, right? Okay, let's turn it off. Now, put the rod inside the solenoid. Just, it'll fit. It was, we worked it out ahead of time. Okay. Now, you remember that for capacitance, the geometry was the primary factor to consider. And then another factor in that geometry was in what material was the capacitor sitting. The dielectric material, what was inside the capacitor, between the plates, if you will, mattered. And if we put material inside the plates, in the common examples we looked at, what happened to the capacitance? Did it go up? The ability to store charge went up, didn't it? Now we've taken a coil that had air inside it, and Amanda has put iron rods in it, not filling it entirely. It's like maybe 1/3 filled with the iron rods. But now, Amanda, throw the switch. Oh, wait. Is the bulb burned out?
I don't think so.
There's a dim glow going off in your minds here, isn't it? Raise that a little bit. Okay, now let's see if we can make some conclusions. You're safe up here because you're helping. They have to answer these questions. If the bulb is dimmer, what does that tell you about the current that's passing through the bulb? I hear less down here. Do I hear more up anywhere? Anybody bid higher? Less is more? If the bulb is dimmer, the current must be lower. right? It took more energy to heat the thing up. We need I squared R to be bigger. We need I bigger. Give us a little more there. Okay, look at that. Go all the way.
Okay.
It's not going to burn that guy out, right? Because it's nowhere near bright enough. Okay, so now she's pegged this thing all the way to 140, the maximum on this, whatever this dial means. And the bulb is not as bright as, okay, you look with your eye for that brightness, okay? Now we'll go back down here, turn it off. I'm going to take this guy out, and now you turn it on and bring it around to whatever it takes to make it the same brightness you just saw. And if we need to repeat, we can.
It was that bright.
Is that I think I'd go with that. And where's the reading on that guy?
About 46.
So it's 1/3 of full setting. 1/3 of full setting. To get the same brightness as when we put the iron in. Are we ready? You ready to watch what happens? I'm going to put the iron in and watch what happens. Now you're going to have to go ahead and raise it all the way up to full. And that's about where you just had it for no iron. So evidently, what's happening here is the inductance is changing because we put iron in. Let's turn that guy down to 0. Turn it off. Okay, I'm going to take this out. You wanted to know what it looked like going all the way with that on. Go ahead. Let's find out if it burns the bulb out or not. Keep going. Excitement builds. Little bright close up, isn't it? That's not all the way. Just do it.
Okay.
Okay, and then we have to stand back because it's too bright. So the intensity your eye falls off is roughly 1/r squared.
Mm-hmm.
So if you step back a factor of 2, it decreases a factor of 4. Unfortunately, the eye sees things logarithmically. So you have to do powers of 10 instead of just powers of 2 to get there. The eye can see dim light, bright light, around 13 orders of magnitude in power, in intensity difference. 13 orders of magnitude. And your ear can do almost that level with hearing. That's unbelievable. You try to make a detector that can cover that wide a range. Okay, here, take that and go like that. Now she's pumping iron. Okay, thank you. What great pumping iron we've seen here. Go on up and get some notes. What we saw here, Amanda was running an alternating current supply, AC. So it means that the current is time changing 60 cycles a second throughout. And Amanda, if you need some notes, there's probably a couple people near you, or come down, get from somebody right down here who make good notes, okay? So the voltage coming out here going to this inductor is changing 60 cycles a second. It means that the flux in that coil is not 0, except at momentary points in that current flow. So that there is a back voltage being created. It means that the voltage drop then across the across the light bulb here, that resistance over at the side, is reduced. It's not seeing 110 volts or 120. It's seeing 110 volts minus the back voltage across this inductor. And then when we put the iron in, the inductance was increased. L was larger. So the back voltage, L was increased, the back voltage increased, and the voltage across the resistor is reduced even more. All of that going at 60 cycles a second. Okay. we need a volunteer. Harry, you volunteered already, right? Did you volunteer? Yeah. We did a female, I got to do a male now. Purple shirt, have you helped? Blue shirt. Come on up, blue shirt. You know, for some sports teams, what do you call it? Your red shirt? Red shirt, he's going to have a blue shirt day. Okay? Oh, this is right. The shirt works too. Okay? Yeah, but look at just face the crowd. Look at this. We got electricity going off, and just do it, right? Okay, I'm Roger McWilliams.
Neil.
Neil? Hi, Neil. Okay. Now, Neil, describe to people what you see here.
Just a bunch of coils.
Bunch of coils. In fact, how many coils do you see if we count them? Here's 1, 2, 3, and
4.
right? See?
Oh, okay.
You didn't know that.
No.
Yeah, okay. And do we see any wires attaching coils at this point?
It's black and
Yep, that's okay. There's a black wire going over from one coil to the opposite side here, and a red wire doing the same to the other end of the coil. So this top coil here is electrically connected to this top coil over here, right? And then, what's that?
it's a magnet.
How do you know?
And there's a north and south.
There's a north and south, so he's got some visual cues that it's a magnet, but you don't really know that it's a magnet yet, do you?
I guess.
Yeah, that's right. And so we want to move from the qualitative stage, where we're guessing, to some kind of actual measurement. Let's see.
Oh, yeah.
Okay, now we've proved it's a magnet, right? Okay, so there's a magnet, and this one is labeled what color?
Green.
Green, okay? And this one is labeled what color?
Red.
Red, okay, cool. And we got our S's pointing down, right? Okay, so now if Neil, is it Neil?
Yeah.
Neil takes that magnet, if you drop it exactly straight up and down, it will oscillate, right? We'll have a spring action. As it passes into the coil, there is a d flux dt, right? There's a magnetic flux from the magnet that Neil dropped, and it makes a d flux dt in this coil over on the side that Neil is at. If there's a change in flux, there's a voltage induced, means there's a current that can flow. There is a wire attached to allow the current to flow through this coil over here. If this coil is flowing over here with current, it makes a magnetic field, doesn't it? And magnets can attract and repel each other, can't they? Drop your magnet again. So if, that's good. That's actually just about right. It just tapped at the bottom. Good for you. That's exactly right. Okay? So what do you see happening on the magnet over here? It's moving now, isn't it? So that magnet is dropping down. Gravitational potential is allowing it to convert to kinetic energy. It's causing a d flux dt over here on Neil's side. That's driving a current each time, up and down, right? It's flipping in time. It's not constant in time, making a time-changing current over here, and that current induced over on my side makes a magnetic field inside the solenoid. That magnetic field pushes on the red magnet over here. Okay, reverse it. Just do the red one instead. If everything is symmetric here, we should see the green guy start to get going as the red one dies down. Now we can add to this if we want to. Since we've got 4 coils here, let's try doing something with all of them, okay? Why not, huh? And what I'm doing is hooking up the bottom 2 coils in series with the top coil. Okay. Give it a shot. Let's see what happens. That's not terribly exciting in any difference, is it?
Mm-hmm.
Maybe this guy's getting going a little better. A little better transfer.
Yeah.
Let's try reversing the direction of the wiring on the bottom coil here and see what happens. Okay, go ahead. Not so much, is it? So if I have the coils wired reversed to each other, this guy at the top is got a little more effect on the magnet than the one at the bottom, but they're kind of opposing each other at this point, and it's not making as big. Okay, is this exciting?
Sure.
Okay. What else could we do with these guys? Oh, that's cute. We got an oscillation running here, don't we? There's a giant spring motion like this, but there's a vibration within the coils going on here. Can you think of where that might happen in your life? You ever drive a car?
Yeah.
The car has valves in the engine. The engines are springs that look like this, and they can get oscillations running in them that are microscopic, just like that, and it can break the valves.
Wow.
Or break the springs. So that actually has to, people design springs to make sure that does not happen. It's a very curious thing. Been around about 100 years. Okay, thank you, Neil. Excellent job. Okay. All right. How would we find what inductance is? When we wanted to find capacitance, we had that C was the charge per volt that got stored. So what we had to do was first find the electric field, find E. Then find V, then find C. To find the electric field, we use Coulomb's law, Gauss's law, right? So we use Coulomb or Gauss. Then we did integral E dot dl, and then we did Q stored on a plate divided by the voltage. Those are the steps to find capacitance. For inductance, it's a similar kind of breaking it down into smaller steps to do each step. If we have that inductance is the flux this is the flux per turn times the number of turns, right, which is equal to flux total per current. Then what we do to find inductance. We first find B, then find flux, then find L. We find B by using Ampere's law. Then we find this flux by the integral, right, of B over the area. We find the flux, whatever that's going to add up to, maybe n times it, right, if you have an n. And then we do the flux divided by the current. So break it down into small steps. Alternatively, if you know how to find di dt, and you can find the voltage, you can take that ratio. So there are two ways that are able to find inductance in this sort of circumstance of way we're thinking about things. Remember this n. It's real easy to forget putting that n in there when you do these calculations. So if you have a single turn like over here, it's not going to be an issue. But when you do a solenoid, you want to include that for sure. Okay, values of inductance are in the units of henries. We had farads for capacitance. And what were some typical capacitance values? A picofarad is a typical capacitance value. A microfarad is a typical capacitance value. A millifarad, we can make those fairly easily. Getting up to a farad is now getting difficult, but possible. So picofarad to farad. Henries, the values of inductance that we typically run across are microhenries to millihenries. In that range is pretty common. Sometimes you'll run across something even bigger, and it makes it really hard to get currents going. Sometimes, let's see, not just sometimes. Did any of you use a hairdryer this morning? Yeah, that was a good one. It didn't take long, did it? So, none of you gals used a hairdryer? When you use a hairdryer, you're turning on a motor, right? The thing's got the fan that gets going. And as it starts right at the beginning, there's a big back EMF, right? It gets going on it. Okay. Anyway, you want to think about motors. Sometimes this stuff plays a role in how much current gets pulled in a motor. And you want to be careful about the design on the motor for that too. Okay, so let's see. Let's do a circuit. And let's take a look at what we've got going here. If I have a voltage supply here, I've got a resistance now and an inductance. Let's just conceptually see what's going to happen with this circuit to start with. Right now the switch is open. So when Amanda had the switch open on the power supply here, was any current flowing? No current's flowing. We close the switch. current will start to flow. If the inductor is not there, the current will flow, the voltage will drop across the resistor. V equals what? We got V equals IR on the resistor. And this guy, we're going to have V equals L di dt. So right when we close the switch, di dt is very large. So most of the voltage drop will be across here, and very little, 0, will be across the resistor. And then as the current builds up, the voltage drop across the resistor increases. So versus time, the voltage drop across the resistor is going to be 0 to start, and then it's going to build until it arrives at V. When it arrives at V, what's the current doing? And this is I equals to V over R. So what we have here at the inductor, the voltage on the inductor is going to go to 0 as the current goes to steady state. So when we close the switch, we'll get a big voltage drop across here as it's trying to build up the magnetic flux inside, and the opposition to that is being done. Then we arrive at all the current providing a voltage drop across the resistor only. So as we started out, we're pushing that charge along, building it up. We're having to do some work here in that inductor to get the flux built up. So we could ask ourselves about the power in that. The power in the inductor versus time is going to go something like that also, because the power is going to be I times V in the inductor, which is going to be I times V. Oh, let's see. V is going to be L di dt. So the power in the inductor is going to depend on the inductance in there. Can we solve it? Can we look at that and see what happens as a function of time? Now you can do the math because you know what the answer is. What's the shape of these curves look like? Look at that upper right one. What kind of decay is that called? It's an exponential decay. So we expect exponential rises and exponential decays. Okay, so we have, if we want to look at the voltage around the loop, so we have L di dt plus I times R. And that's going to be equal to V at the battery. Do you know how to solve this kind of equation? Let's look to start. Look first at maybe we can simplify that guy a little easier. So we see from that guy that if I write it this way. And I see the current. Oh, the current. di over I. Integral di over I is minus r over L dt. What is the integral of di over I? Logarithm, right? So we have the log of I from I0 to I final is equal to minus r over L times t. We exponentiate and we see e to the minus t over L over r. So I goes as I naught e to the minus t L over r. If the voltage was 0, any current in the system, if the voltage was 0, the current that was in the system to start gets dissipated by the resistor. So if we had 0 to start, then, but if suppose we had current, but we got rid of the battery, the current will slow down because of the friction in the resistor, and it will slow down at that rate. Now if we add the battery to it, that physics is still going on. The resistance is trying to dissipate the current, but the current is trying to build up because of the battery. So we get, when you have the battery voltage added to it, that the current will have two components to it. The steady state, V over R, plus this contribution, which dies away. So the current builds up, like we've drawn in the upper left, when you replace this 0 with the V battery and solve it. Now I want to look at a different circuit element and think through a little bit of the physics in it. Let's draw for comparison same circuit with a resistor and an inductor. The inductor opposes the change in time, right? And the resistor dissipates the energy. So any current that flows in this thing will go away with the resistor there. Now let's make a circuit with an inductor, but replace the resistor with a capacitor. If there's current in this, the current will flow over towards the capacitor, builds up the charge on the capacitor, does not dissipate energy. It builds up the charge on the capacitor, and then when the inductor can't oppose the push anymore, we've got the charge over on the capacitor going, wait a minute, we can go back around in the wire to neutralize, and the charge will turn around and flow the other direction. This circuit doesn't dissipate in time. The current will not go to 0. Instead, on this circuit, the current will oscillate. Because what's happening is the energy is being stored in the capacitor. The current flows. When the current is maximum, then we have energy maximum storage in the inductor. The energy stored in the inductor goes as a half Li squared. Take a look at what I wrote for power there and do the integral with time. Integrate the power over time, and you arrive at that, right? U is equal to integral power dt. So you get energy stored in the capacitor. We had that, or the Q squared over C, right? That's whichever one you want to use. And the energy then rings back and forth. So this is a circuit that does not dissipate, but it oscillates. And if you want to make an oscillator, that's a right, easy way to do it. If you want to dissipate current, you use the top one, and you can choose the time. This time e to the minus t L over r. Here's the time it takes to go one factor of e down. It's called an L over r time. You vary your L's and you vary your R's, and you choose how you want your current to go. Now what happens if we start putting inductors in series and inductors in parallel? What happens if we put inductors, capacitors, and resistors all in the same circuit? And then what happens if we put AC, the Paul Revere thing, right? What happens if we put AC on it? Does it get maddeningly complicated? Yes, it does. And then you turn to an electrical engineer and say, please help with this. And those guys make bank because the electrical world is very important to you guys, right? It also happens inside your bodies. You've got anywhere that the nerves and things are flowing, currents going in your bodies, there is a capacitance, there's an inductance, there's a resistance. It does describe the physical activity of your body down at a microscopic level. It's very good at it. And then you throw in some chemistry stuff too, right? Okay. On this chapter, the last third of the chapter is a miserable amount of phasors and various AC circuit things. I'm not going to ask you that stuff on the final. Whew, right? I'm not feeling crabby today, right? So what we're going to do is focus on the physics. What causes this to happen? The way I've been describing it today. You should be able to put inductors in series and parallel. Learn a little about that, okay? On Monday, we're going to go through all this equations as a cumulative organized set and review things.